Hello, today we're going to talk about Reactivity 3.2.12 and 3.2.13. These are HL topics only, and they have to do with the standard hydrogen electrode and using standard cell potential. Okay, so let's start out by talking about electromotive force, or EMF. It's the potential difference. And for chemistry, we're going to abbreviate it E cell because we're dealing with electrochemical cells. And again, in chemistry, we're going to look at the difference in tendencies to undergo reduction. So some half cells are more likely to be reduced than other half cells, and the difference between the two half cells when they're connected gives us the overall cell potential. Now it's measured in volts, which is joules per coulomb, and so it's energy per electrical charge, basically. Now, when we have the cell potential for a particular cell, it can either be positive or negative. If the overall cell potential is positive, then that is a spontaneous reaction, spontaneous redox reaction. And that means you do not need to input any energy for that to happen. So we're typically looking at voltaic cells for this. If your overall cell potential is negative, then it is a non-spontaneous redox reaction. And that means you have to put in energy of some kind. So that is typically an electrolytic cell. And it's the value of E cell will be different depending on the half cells that you connect together. So like zinc with copper is going to have a different overall potential than zinc with manganese or magnesium. So you have to look at both half cells when you're putting together the overall cell. Now, in order to be able to measure cell potential, we have to connect it to a standard. So we use a standard called the standard hydrogen electrode, which is abbreviated as SHE, or SHE. I usually just say standard hydrogen electrode, but it's effectively you have hydrogen gas being produced. And the hydrogen gas is produced at 298 Kelvin, 100 kPa, so standard temperature and pressure. And you'll typically use an inert platinum electrode. And it's usually going to be in an acid solution that has a 1 molar or 1 mole per cubic decimeter solution of hydrogen ions. And so this is our reference half cell. What then you'll do is connect this to some other half cell and see what the difference is. And that becomes our standard value for the other thing, whatever it happens to be. Okay, so we talked about the standard hydrogen electrode, and we measure a bunch of other half cells against that standard hydrogen electrode. And from that, we create a chart of the reduction potentials for a bunch of different half cells. And another way to abbreviate that is like this, reduction potential. This little symbol at the top here just means that it's at standard conditions. And there is a big old table of values for reduction potentials in your data booklet in section 19. And so all of the half cells in your data booklet in section 19 are all measured against the standard hydrogen electrode. Okay. So what can we do with that information? Well, if we know how each of them are compared to the standard hydrogen electrode, then we can use that information to help us figure out if you connect any of the other half cells to each other, what would your overall cell potential be? And of course, these are at standard conditions. So again, this is going to be in 1 mole per cubic decimeter solutions, which is a really important one to remember. That one can throw you off sometimes. It's funny, 1 mole per cubic decimeter. It also should be at 100 kPa, 298 Kelvin. If you're using an inert electrode, it should be a platinum inert electrode, but a lot of times you'll be using the metal itself that you're testing instead, so it won't be an inert electrode. And then, of course, you should not be using mixtures. Aqueous solutions, yes, but not mixtures of different substances. So those are your standard conditions for cell potentials. And then we talk about, now that we have these reduction potentials, we can start connecting half cells to one another. The overall standard cell potential is equivalent to the standard reduction potential at the cathode minus the standard reduction potential at the anode. And remember that the reduction is happening at the cathode, so that's why this term is our positive term, because the reduction is happening just as it's written. Our anode is going to be subtracted because it's not reduction that's happening at the anode, it's oxidation that's happening at the anode. So we have to flip the sign, or subtract the reduction potential from your data booklet in order to find your overall cell potential, excuse me. Another way that you could do this, and this way that I am kind of fond of, E-cell, is I'm taking the reduction potential for the cathode plus the oxidation potential at the anode. It's another way to think about it. Just the table of values in your data booklet, section 19, those are all reduction. So to get the oxidation value, you change the sign. So either way you want to think about finding the overall cell potential works, subtracting the two reduction potentials or adding the reduction to the oxidation potential. So again, with the standard reduction potentials, they're given in your data booklet in section 19. And you can also compare those values to one another. The larger the value of the reduction potential, so the more positive it is, the more likely it is to be reduced. The more positive value, more reduced. The smaller the standard reduction potential, or the more negative, the more likely it is to be oxidized. So that also means that the highest values, the most positive values, are the best oxidizing agents. And the more negative values are the best reducing agents. So that's another way that we can use those table of values to compare the oxidizing or reducing ability of the different half cells that are listed. Okay, so let's look at a couple examples. We want to calculate the electromagnetic force for a voltaic cell constructed from a zinc half cell and a copper half cell, and identify the anode and the cathode. So you need to look in section 19 in your data booklet, and you'll find we have our copper going to solid copper. The cell potential for that, the reduction potential for that, is positive 0.34 volts. And for the zinc ions, going to solid zinc, the reduction potential is negative 0.76 volts. So in order for us to have a voltaic cell where it's spontaneous, we want the overall value to be positive. So that means that the more positive one is going to stay that it's going to be reduced. It's going to be at the cathode. So the copper will be our cathode. The zinc is then going to need to be oxidized and will be at our anode. So what you'll do is you'll go ahead and flip the zinc reaction around because we need it to be oxidized. So its oxidation potential is positive 0.76 volts. And to get the overall cell potential, standard cell potential, you're going to add the reduction potential to the oxidation potential, and you get positive 1.10 volts. It's the same thing as if you did 0.34 minus negative 0.76. I just like thinking of it in terms of oxidation instead. Oh, it also wants us to find the overall reaction, so we need to just combine the two, the cathode and the anode together. So you'll do the Cu2 plus ions plus the solid zinc, forming solid copper and the zinc ions. The electrons cancel out. So there's my overall reaction, and the cell potential is positive 1.10 volts. Okay, so we need to use E values to determine whether this reaction will occur spontaneously as written. So I have my manganese ions. I'm just writing it as half reactions now. And the other half reaction is my nickel going to nickel 2 plus 2 electrons. So this one is the reduction reaction. And if you use your table of values, the cell potential is negative 1.18. And for nickel, the reverse reaction is negative 0.26. So my oxidation potential is positive 0.26. And so when you add those together, you will get a negative value. You don't even need to find the exact value here. I know that this negative value is larger than the positive value. So when you add them together, you get a negative value overall. So it will not be spontaneous under standard conditions. Okay, we need to identify the strongest oxidizing agent and strongest reducing agent from the following. So in this reaction, this one is most likely to be reduced, which means it's the strongest oxidizing agent. So it causes other things to gain electrons. And our second one, the magnesium, because it's the most negative, it's more likely to be oxidized. It's going to be our strongest reducing agent.